Yes.
Okay, so our next speaker is Edoardo Vescovi, who's going to talk about correlation functions of determinant operators in conformal Fishnet theory.
Thank you very much for this kind invitation. It's a pleasure to be here and present my work with Omar Shapo, a former master's student in Imperial College and now PhD in King's College, London. It's a work about fishnets. So to get everybody on board, I just remind fishnets are models, quantum field theories, where endpoint functions are described by Feynman diagrams with the topology of a regular lattice. We're going to focus mostly our attention on the square bosonic lattice, underlying the bi-scalar fishnet theory. Here, the main protagonist is the fishnet vertex. This sets the basis for most of the properties, directly or indirectly, that this theory has, starting from integrability, also in connection to an integrable lattice spin chain model. It is an integrability that really stems out of the diagrams. It is more direct and transparent than that in n equal 4. That, of course, underlines many techniques based on this integrability. It also ensures that the theory is a conformal field theory in 4 dimensions, so it is a rare and unique case in more than 2. And many other properties, like the Youngian bootstrap that we have seen this morning. Actually, the fishnet itself, strictly speaking, is not conformal. You had to add double trace counter terms to make it so. These are the so-called minimal size effects. They enter these counter terms. They needed to be added, and they appear whenever you have length 2 operators in the diagram. This is to stabilize the RG flow, to make this theory fully conformal. So this is the bi-scalar fishnet with only, as the name suggests, only 2 scalars corresponding to these sets of lines. It is a particular case of a more general fishnet, actually. I'm going to refer to that as three-coupling fishnet. People also call it chiral CFT4. Yeah, just a name to remind that it has 3 coupling constants, but more importantly, you're also allowing fermionic lines. So it is more complicated. You have 3 scalars, not only 2, and also 3 fermions, and 3 coupling constants, not only 1 associated to a single vertex. And in turn, just to finish this review, this theory is a particular limit of a more general theory, very well known, which is n equal 4 super-M-Mills with gamma deformations. If you go to a particular corner of the parameter space, you recover this beautiful fishnet. And again, if you can go back by setting 2 couplings out of 3 equal to 0, you go back to the bi-scalar fishnet. So the conclusion of this first slide is to make this question. So if all the physics of the fishnet is so encoded into the graph structure, how do we compute different observables? Let's focus on correlators. What you have to do is to carve out a finite size lattice along a certain curve. This will define a certain sequence of fields. This, for instance, will describe a certain single trace operator with this sequence of bosons, the phis and the psis, the fermions. These are the typical correlators that have been considered so far. The very general question that we started with the student was to ask what happens now if we consider operators that have they contain many operators that have a dimension that is not of order 1, like in this picture, where you have a dozen of fields, but instead it scales with some powers of n. And if you ask this question in n equal 4, you can have many choices. You have scaling like linearly in n or n squared. This corresponds to a variety of operators. We stayed very pragmatic, and we went for the first category, so linear scaling in n. And among this huge category of operators, we focus our attention on the determinant operators, for reasons that I'm going to explain in the lower part of the slide. These operators are defined, as the name suggests, in terms of the determinant operators, determinants of scalar fields. I call it phi generically. These are local, engaging invariant. You can expand them in components. The fields with the gauge indices are contracted not to Kronecker deltas to create traces, but they're contracted with epsilon symbols, so plus and minus 1s. I denote with phi a generical combination of the scalars. The y is the so-called polarization vector. It is a 6-dimensional vector, an array of numbers. And whenever you take it to be null, these operators are 1/2 BPS in the mother theory, in n equal 4 super-Mills. They've been extensively studied also in holography. They correspond to maximal giant gravitons, D-branes wrapping an S3, stabilized by angular momentum, which is maximal, satisfies a bound. This is why they're called maximal giant gravitons. And the reason for revisit this story, these operators, stems in one motivation that I want to bring up, stems from an observation that in this paper with my collaborators, Yunfeng and Shota, we made in a paper years ago when we were studying correlators, 3-point functions involving 2 determinants and a single trace. There are certain cases in which this expression can be rewritten in terms of an interval of Q functions. This is an interesting observation because there are many other variables of quantum level that can, in Gauss theory in n equal 4, that can be written in this form. And it is, so this gets added to an ever-growing list of such observables. And this form is interesting because it seems to suggest that maybe one can apply some sort of SOV method, separation of variables method, to obtain them in this form, indeed. In integrability, SOV is very popular because in essence it gives you a chance to have a full quantum control on your observables because the Q functions are very well known and studied at finite coupling. At the same time, we also know from Fishnets that we had a lot of developments coming from lower rank interval spin chains, as well as the Fishnet itself studying SOV. So in some sense, determinants may sit in a sort of sweet spot, and they can further advance the study of SOV. This is a long-term goal to keep in mind. I want to bring up 2 other motivations before starting. In literature, people have also constructed deformations of determinants by replacing a letter with a word, a product of fields, including covariant derivatives. That is to say, an open spin chain, you see from the indices. The spectrum is usually non BPS. People have studied these objects, also with integrability. This list of references is very conservative. There are many works in this direction over the years. And holographically, if a determinant creates a giant, these creates they add open strings and ending on giants. And there have been a series of papers where people have actually constructed explicitly the worksheet of these open strings, and they obtain a match and a map between the energies of strings and the anomalous dimensions of these operators in some larger charge limit where this matching is possible. Here, the hope is that by studying operators and getting full control on them from the Fishnet point of view, where this task may be possible, maybe we can also say something about the holographic duals and expand our dictionary beyond the current models that we have. The last point is more generic, is about large N quantum field theories. It stems from the analogy, the similarities that we have between determinants of scalars, with matter in the adjoint, and baryons, like in large N QCD, where you have matter. These are color singlets of quarks, so particles in the fundamental. Here, the objective would be to study these operators in these Fishnet theories, where the graph content is particularly simple, and maybe hope to derive some systematic way of resumming the loop expansion. In a theory, again, we also have an handle on these correlators, potentially from integrability. This is a very broad perspective. Now, I want to start to tell you exactly what we have accomplished. So in the first part, I want to make some general questions about the perturbative structures of these correlators. Because if I told you that we had so many techniques coming from n equal 4, both in Gauss theory and in string theory, now the question is, what are the additional challenges that Fishnets pose to the study of these operators? So both in the mother theory and in the Fishnets, it's useful to refresh our memory and remember that determinants as heavy operators lack a standard notion of planarity, the usual expansion in ribbon graphs. This is easy to understand if you compare the two-point function of single traces and the two-point function of determinants. These two-point functions are protected, of course, but that's not the point I want to make. I want to make comments about the large N expansion that is applicable for all states, also in the Fishnet. So when you have traces, of course, you know that the trace naturally defines an order among the fields. So the leading N contribution is simply a planar diagram. You have to draw all of them. This ensures this is leading in N. For determinants, the story is different because there is no naturally an order. They are defined by epsilon tensors. You can swap fields. The worst thing that can happen is getting a minus sign. You can, of course, decompose them onto traces, multi-traces, but the catch is that they would belong. So to the leading order in N, there would be both planar and non-planar diagrams contributing. This is a very well-known fact coming from the early days of ADST and these heavy operators as well as a large NQCD. So there are combinatorial effects. There is another combinatorics, huge combinatorial factors that non-planar diagrams carry, positive powers of N, and they usually overwhelm the natural 1/n suppression of non-planarity. So these diagrams come up in N, and they contribute to large N. This is not a big deal in N=4. It is hard combinatorics. But what happens instead when we go to the fishnets? Because as I said briefly at the beginning, the conformality is well established only for the planar fishnet. So what does it mean? Does it mean that we have to, that these correlators of determinants would lose their conformal properties? Does it mean that we have to first preliminary study the renormalization of the theory beyond the large N limit, more fundamental first principle problems? And the answer to these questions turns out to be negative if we think a bit more carefully about the expansion of these correlators. Let's focus on, again, on a generic example. I will have some graphs of some specific correlators at the end. So let me denote the scalars with the generic names. This also applies, some considerations also apply to the mother theory. The way to answer that question is to proceed with some methodology, some wise methodology, to carry out the weak contractions. Suppose that you just have a determinant pair. You can first operate the free weak contractions among the scalars over here. And if you do that, well, you can operate all the weak contractions and obtain simply the tree-level two-point function. That is not super useful because this would lead to some disconnected contribution in a higher point function. But anyway, the contribution stays there. Or you can instead operate n-1 weak contractions between the determinants. So this leaves a pair uncontracted that gets organized into a single trace of length 2. Or you can also have longer contributions. Suppose that you only take n-2 contractions. So 2 contractions are left. So you have 4 fields from the determinants left uncontracted, and they organize into these length 4 contributions, a single trace and a double trace. And the same play can go on. The key observations here are actually 3. One will be useful for later. You see these intermediate states have these projections, have an alternating structure, 5-5 dagger. So you have always a scalar from the first and a scalar from the second, and the pattern repeats also in longer traces. This will be useful for later when we will consider some actual diagrams. For now, the considerations are, the key observations are 2. One is that all these terms carry uniform powers in N. There is no enhancement that one trace would have compared to others. And all these traces are short. So this is the actual traces that we have to consider are short traces. And this is useful in the second part when we finish off these contractions. For instance, when we overlap this pair with this length 4 and also with interaction vertices. We are in a fully interacting theory. At the end, we only have to consider short traces. So the conclusion is that after these wise contractions, you realize that from the bulk point of view of the graphs, we're going to say something about the boundary later, but about the bulk topology is the same planar fishnet in the common traditional literature. It is to say regular lattice structure, potentially decorated with the planar counter terms, but these are the usual planar counter terms that I said at the beginning that ensure the conformality of this graph. So they have, of course, the same property of finiteness, conformality, and also integrability. So this potentially paves the way to use integrability for these operators as well. While I still keep this picture, I make a few other comments. I don't want to sell the idea that, nevertheless, this method is convenient from a practical point of view. That is to say, really with pen and paper, or even with the help of a calculator, for a number of reasons that also marks a difference with the traditional literature of fishnets. First, notice that here the lengths of these intermediate states are not fixed. This little l, that in this case was equal to 4, this state up here, this index is a running index. You may have different contributions, and a priori, just by looking at the correlator written on paper, there is no really way to understand which of them, if one or more of them will contribute. You have a bit to sit down and empirically work out what are the intermediate states that may enter. It is not said, as the picture may suggest, that if you have a certain length of an external state, this will uniquely fix the length up here. You may have different contributions. We'll have an example later. And a problem related to that is that you would also, since L is running, you may also have L equal to 2 over here, so this term over here. And this will imply that on general grounds, you don't really have a direct way to exclude from the get-go the appearance of double-traced vertices. I stress, these are the good double-traced vertices. This is different from the traditional literature of fishnets, because usually what we do in most of the papers, if we want to go to some simplifying limits, we don't want to consider lattice impurities. We simply set the lengths of the operators all greater than 2, and we will have the wonderful regular fishnet. Here, potentially, there are always minimal size effects behind the corner that may appear. The third point is related to the complexity of this procedure. Going to the three-coupling fishnet or considering determinants of combinations of scalars will bring a complexity that is beyond normal control with a proliferation of diagrams. So while it is technically clear, it is in practice complicated to carry out. And for that reason, I want to explain an approach that was already in the idea and in some form in the paper with my collaborators. But we expanded this method in 2 directions. Before I present it, I want to say what are the improvements so that we can see them in the next slide. So in this method, we are going to, of course, bypass all the technical limitations. What are the changes with respect to the past? We have a method that can include all the interaction vertices, potentially an arbitrary number. It is only limited by computational power. So this generalizes the approach that in the original paper was only at 3 level. And the second is that we implemented the formulas that I'm going to show in an algorithmic way in a mathematical script. So you can input your external states, press Shift-Enter, and this will produce the corresponding diagrams. I'm not going to go through the derivation of this method, but at least I want to tell what is the flavor and also how it can be applied beyond fishnets potentially. So the idea is to rewrite the correlator of determinants in an alternative form that is more manageable. Rewrite the quantum field theory path integral as a matrix integral with auxiliary degrees of freedom, and integrate out the physical degrees of freedom in some careful way. What are the degrees of freedom first? You have bosons and fermions. You have this row matrix, which is an m by m matrix. The size is determined by the number of determinants. And you also have a row hat, which is a sort of element-wise rescaling of row. This carries information about the polarization vectors and the positions of the scalars in 4 dimensions. I also stress that this matrix is constant, so no space-time dependence. So in this will be a matrix integral, not a QFT path integral. Likewise, the same comment for the xi's, xi bar and xi. These are auxiliary fermions, and you have, if you look at the indices, you have a pair of them for each determinant. The reason is simple to understand, because in one of the steps you need to trade the determinants for Gaussian integral, for Grassmann integrals. So you need a pair for each of them to play this game. I want to flash what are the ingredients inside. So you have an action that is quadratic, and it has also some non-linearities. It is simple to solve because it carries a power of n in front. So you can do saddle point expansion. And by the way, in fishnets, we are precisely interested in the large n limit. So really, this is not an approximation. This is what we want to do if we want to stay in the conformal fishnet. And the super interesting part of the integrand is this prefactor. If I have to describe it in words, I would say it is a sort of the multi-trace O of short length that I put here, but surrounded with all the possible, with a cloud of all the possible interactions before actually these interactions connecting to the determinants. Mathematically, it is defined by this quantum average. This is how the degrees of freedom are, the physical degrees of freedom are integrated out. If not for these shifts, so the scalars in the multitrace are shifted by these matrices S, I will say later who they are, and also in the interacting part of the Lagrangian. So Yukawa, quartic vertex, and double traces, but not in the free part. This comes from some Gaussian integration that you have to perform, some shifts that get eliminated in the free part. This object, this is the first improvement. This object is fully defined at finite coupling. Of course, to calculate this object, it is very prohibitive and daunting to do, actually, at finite coupling. So the strategy will be to expand it perturbatively. I will make another comment on this O. First, I want to say who is this S. So S, the S's are matrices. They have an index J, so you have S1, S2, S3, because you have the three scalars. And they are matrices with indices A and B that come from this product chi bar, which is not a bilinear. If you got lost at this point, I just want to tell that all in all, in this matrix integral, you just have a rho appearing. This is the only integration to do in the last step, because this O, despite depending on this sort of classical backgrounds, these S's, so on these fermions, the fermions are integrated out via some Feynman rule, via this fermionic average that appears in here. So this is perfectly calculable and implemented in an algorithmic way. It can also be generalized for other operators. I will say something later. The final comment before transitioning to the next slide is to remember that in the previous paper where we studied certain three-point functions, it was exactly this object, OS, that could be rewritten into some nice form. We were studying two-point functions of two determinants, and a single trace. And in some cases, we could rewrite this three-point function, which is essentially this piece, as an overlap between a convenient matrix product state and the spin chain state corresponding to the single trace. And this was leading to some considerations about the integrability of a pair of determinants as an integrable boundary state. I mentioned this in connection to the previous paper. We didn't do any investigation of this kind in the publication, but certainly this would be the point to start with, also for the things that I'm going to say in the last conclusion. Okay. M is a convenient matrix that contains, again, information on the y's and the x's. So it has a certain definition coming from those. Yeah. This is just a rewriting of the result into this nice form, expanded form as an overlap. All right. Again, if this is confusing, maybe let's say, what can we do with that? Can we just work with determinants? Can we do something else? What is the actual output if you have to use it? So not only we can study determinants, but we can also play a little bit with the polarization vectors and consider some deformations of determinants. This is a procedure that was used, for instance, in this paper about 4-point functions to control the flow of R charge in certain channels of the 4-point function. And the idea is simple. If you consider a determinant of phi 2, so an array of phi 2s and phi 2s, and you want to replace one letter with phi 1, you can prepare this state and then take a derivative with respect to A1. This will pick up one phi 1, and then when you set A1 equal to 0, you will eliminate A1 together with phi 1 in all the others, so only phi 2 will remain. So we can consider also this with the current technology. And we can have a look at an example. If we take these two deformed determinants, which is this part of this simple exemplifying graph, and we overlap it with this length 2 state, phi 1 dagger, phi 1 dagger. This is an example of diagram that you may have. You have a double trace over here and two single traces over here. This I have to be clear, what the effective theory computes is the unintegrated diagram, that is to say this integrand, this product of scalar propagators in this case, with the correct powers of the couplings, of course. And this is a sketch that I took from the mathematical code, where you also have an idea of the topology of the diagram in X space. So it is up to you then to manipulate this integral. You can do maybe Bethe-Salpeter summation of the diagrams, where you don't need some explicit regularization scheme, or you can just do perturbation theory. This is up to you to decide. Equipped with this tool, I want to proceed to some parts that are more interesting maybe from the physical point of view. That is to analyze some correlators with this tool. The study for now is limited to the bi-scalar Fishnet, precisely for the diagrammatical complications that these operators present, and also for our current implementation of the calculator. Still, it is challenging, and all the challenges in ultimate analysis come from the breaking of the R symmetry SO6 down to U1 cross U1. The downsides are essentially two. Since we don't have SO6 anymore, there are operators that used to be related by SO6, but now since this is not a symmetry anymore, they won't be related by symmetries, so they will behave distinctly quantum mechanically. So you have to consider the correlators separately. This creates a zoology of potentially of correlators. So you have to make some wise choice in order to keep the survey conservative. We still can keep this condition, although since we don't have the supersymmetry, we don't really mind relaxing this constraint if possible. The second drawback is the loss of supersymmetry. This creates many extra challenges because determinants are no longer protected. On general grounds, you can think that may acquire anomalous dimensions. This is in total analogy to the BMN vacuum, which is no longer a vacuum state. It has anomalous dimension in the Fishnet. And about their correlators, while 2 and 3-point functions of BPS operators we know very well, they're protected. Now already the problem of 2-point functions potentially can become extremely cumbersome. So if you were to proceed perturbatively, what you would do, also in the literature of Fishnet for some single traces, what you would do would be to compute the 2-point functions, extract the missing matrix, so filling all the entries, all the possible transitions, and then diagonalize it, or better, to decompose it into Jordan blocks. This is a logarithmic CFT. Now the procedure for these determinants is complicated by the extent of the potential operator mixing. They potentially mix with other operators that are spinless, same bare dimension and R charges. These operators, if you don't have a guideline, they can come in a very large number. It is difficult to get an handle on them, unlike some examples done in the Fishnet for short operators. And there is also technical limitation, because speak about 2-point functions, we cannot, with the current technology, handle transitions from determinants to other sort of operators that are not determinants. So the spectral problem certainly requires a lot of attention, a lot of insight. We didn't go too much deep into that, although we make some considerations and we argue some considerations in the paper. But it's still fairly honestly beyond our control. Certainly this is a pressing issue that would require more study ahead. I want instead to say, from a qualitative point of view, how we can assemble 3 and 4 point functions, leaving aside these problems of discussing anomalous dimensions, identifying primaries. Okay, let me sketch some pictures. We have a bunch more in the paper. To keep the survey very simple, we took always a pair of determinants or determinant-like operators, and we always added a single trace. Single trace that can be of length 2 or greater than 2. These cases must be considered separately for their diagrammatical properties. There are cases that are non-trivial, but go back to cases that have already been studied in the traditional literature. If you insert an insertion each, phi 2 and phi 2, in this pair will effectively contribute with a len 2 of this sort, phi 2 trace phi 2. This is a bilocal operator of minimal length. And due to asymmetry, so R-charge considerations, you can, for instance, overlap it with this, phi 2 dagger, phi 2 dagger. This goes back to a case that was analyzed in the literature. I don't want to say too much about that. It was the simplest 4-point function that was exactly solved and resummed using Bethe-Salpeter equation. It was written explicitly as an analytical function of the couplings. There are cases that are less trivial, brings more complication in the game, like adding instead phi 1 and phi 1 instead. So you can certainly have a class of diagrams where the pair of determinants will contribute this len 2 effective state. And this will go all the way down to get contracted with this phi 1 dagger, if we insert this as a third state. And this is precisely the same class of diagrams that also enter here. But we have a huge variety. We have a second class where now this pair will contribute with the len 4. This is exactly what I was saying at the beginning. It is not set in stone that whenever you have, for instance, a len 2 on the other side of the chain, this will can only overlap with a len 2. You can have a variety of operators that can overlap with this and create very complicated graph structures. I can make more considerations on these diagrams, but I prefer to make, they would hold the same on this. I want to say the same, having a look at more complicated operators. Now considering operators of length greater than 2, like these multi-magnon chiral states. You can prepare these states, phi 2 dagger and phi 2 dagger. These are pure determinant. And then insert very carefully insertions. And again, if you're not careful, the diagrams tend to have a complexity that goes beyond control. So you have to be careful, for instance, adding phi 1 dagger in number L divided by 2. These are the diagrams that come out of this 3-point function. So I spread out around the circle here the contribution that stems from the determinant pair. And in the middle, I place the multi-magnon state. So all around here, what is the state that will contribute? Well, for planarity, since it has to contract a single trace, for planarity, I will have a length L, or in this case, a length 6 intermediate state. And not only that, since there is this strange alternation between phi 1 dagger, phi 2 dagger in x1, x2, all around here. We made this observation in the very first picture when we were describing diagrams. So since we have this alternating boundary of this lattice, this will enforce some conditions on O in order to have a tree level. That is to say that the phi 1 and the phi 2s must alternate. This is an example of T-level diagrams. Of course, this can renormalize, and you can have the usual spiral graphs of the traditional literature. but again with some differences that would make these computations, I think, challenging, certainly different from those seen in the spectrum of the fishnet, where the same diagrams topologically they appear, precisely due to this boundary, which is alternating. These propagators do not end on the same point at infinity. This is not a two-point function, but instead they have this strange alternating pattern. And of course, I remind you, this is a non-trivial observation, that if you were to proceed perturbatively, remember that you're not interested in computing divergent parts of these diagrams. You're interested in, for instance, computing the renormalized finite structure constant perturbatively. So some operations that are performed on these spiral graphs in the traditional literature, they cannot be immediately applied anymore so straight away. For instance, amputating the outer propagators, because this will likely change the finite parts. So if you were to proceed to compute these correlators, you would need to be very careful and to generalize the current techniques that we have, despite the fact that, of course, it is the same kind of planar diagrams, fishnet diagrams. I probably have a last example before I say something more about works and other future directions, promising directions. This is another example where you can be even more creative and insert insertions in both, again with a wise combination, a wise choice of the numbers. The same, here you have more categories of diagrams. This is one. For the same arguments I said before, you will have a planar a single trace contribution from the pair. And again, this will enforce some R-charge assignments on the scalars. In this case, for instance, it turns out that the phi 2s must be separated by an odd number of the phi 1s. This is again related to this strange condition put on the boundary outside by the heavy operators. The same considerations again would hold also for this, and the same also for the matter of computing these correlators, either perturbatively or with techniques based on integrability. There is, I think, a number of future directions that I want to go through with you in the final minutes. So first, this is a very open survey, and really the first step, what we have seen, of getting an handle on operators that are not single traces, also exploring other operators in gamma-deformed and equal force superior mass, in the fishnet limit at least, when they have a large R charge. In this general survey and overview that we started, there are certainly a number of pressing issues. First, the spectral problem. This is interesting because you would, from a, say, mathematical point of view, you would be able to quantify these anomalous dimensions maybe exactly as it was done for single traces. But also in the light of some analogy that I made at the beginning, in some sense, extracting anomalous dimensions out of these two-point functions would be equivalent in some sense to measure the mass of baryons from their two-point functions. So maybe you can also think of developing these diagrammatics and enrich it in order to pursue this analogy. Certainly, once this problem is fixed, you can continue exploring the survey and continue studying some particular correlators that are promising than others. Our survey was very broad and general. That was just a selection of the most sensible results. Of course, there's a huge deal of conformal data, also structural constants coming from it. And very likely in this business, you will have to use techniques of resummations. I didn't say a lot about them, but they always involve some effective operator, a graph building operator that applied many times will build the graph for you. And due to the fact that these pairs of determinants, they do not give a state of fixed length, it can be of any length, maybe this will be another direction for studying, that many people have taken over the last years to study some particular fishnet integrals. Now the boundary conditions would be different, but maybe some of the same techniques would be applicable as well. There are further directions in integrability to search for integrable boundary states that is so popular nowadays. In a survey by these authors, only giants in n equal 4 seem to be integrable in n equal 4 among a certain class of heavy operators. Although we shouldn't be too pessimistic because we can also throw into the game open strings. Open strings on maximal giants have a dynamics which is integrable, whereas to my knowledge there are some mixed indications about open strings on non-maximal giants. So it would be worthwhile also to have a look at those, maybe in the fishnet. Of course, we can also go beyond the usual fishnets, have a look at BJM, where determinants, subdeterminants seem to be integrable. Maybe there's in other interesting directions in the fishnet of the BJM, and also in these fishnets of n equal to 2 superconformal field theories in 4 dimensions, where very, very little is known, but it is very interesting from a physical point of view because it cuts out an integrable sector in these superconformal field theories. And maybe this search for integrable states can be very, can bring many results also to in this sector. I finish with holography by saying that a huge important thing in the traditional literature was to explore the large coupling of 4-point functions because this led to indications that maybe an holographic description that we know by now is the fishnet could have been possible. So maybe with this you would discover some nice semi-classical scaling that would hint at some brain-like description, some sort of expansion of the fish chain. And certainly have a look at something that I said in my introduction about try to reproduce these open strings from the ground up, matching string energies and anomalous dimensions. So this is very rich as a follow-up, and I can stop here with my talk. Thank you very much.
Thank you, Edoardo. Do we have questions?
Very nice talk. And I wanted to ask you if you try to explore some special kinematics for higher point correlators between determinant operators, or rather, if you try to study problems similar to that of higher point 1/2 BPS operators, but instead of trace operators, determinant operators, since in that case we know nice results in the trace case.
Yes, so I must say, I think that all quantitative results are a bit subject to this problem of mixing, to properly identify primaries and also calculating dimensions first before going to higher point functions. So far we didn't do any investigations of this sort, precisely because of this limitation. But it may be possible, maybe you can, yeah, we thought a little bit also in the publication that I had in 2021. Maybe there are some cases where you can decompose these determinants onto a set of traces, maybe not just 1 or 2 traces, so they would become some trivial cases, but a set of traces. Maybe there you would have some connections with those results, but that is an avenue to pursue. I cannot say something quantitative, I must say.
Thank you.
I have questions. Fedor has a question.
You mentioned in the beginning some expected relations with separation of variables and with results from our papers.
Yes.
On that. So do you already see any hints of structures of SOV from your calculations that you've done?
No, but you could by, for instance, taking as a starting point 3-point functions involving only 2 heavy states and putting a probe, the local single trace operator. You would be able to do that, and that would be probably a beginning also to see some, even before that, some matrix product structure state. That would be, I think, the next immediate development of this, also the effective theory that I presented. I must say, already the building that was very cumbersome and lengthy in time. So we didn't, that would be immediately the next step anyway, using that, that comment that I made.
More questions? Yeah.
I was wondering, this insertion of one type of fields into the determinant operator, it looks very much like these sure polynomial operators of the South African group. Maybe you could comment on that?
I understood the short polynomial operators. If you can apply the same techniques you said.
I was asking if it's, in what way is it different, the way that you insert some
yes.
different fields in your determinant operator? It looks very much like the construction of these sure polynomial operators of the South African group.
Yes.
So can't you use some of their exact results, because they have some exact finite n results for these sure polynomial operators? And
you can certainly apply the same logic to those operators, yes, and build a generalization of this effective model. But you said also finite n. I didn't catch.
They have some finite n results. I was just wondering
right.
if you're somehow doing something like what they did in practice.
Finite n is something that we don't want to touch in the Fishnet. We just want to stay at large n for now. I mean, it all boils down if the Fishnet can bring, some more insights, some different results. For instance, exact resummations of diagrams, because this is the whole point in working the Fishnet. You have this hope of resumming interacting diagrams. I think that would be the addition, just instead of just repeating a similar calculation, but to see if you can bring new insights from exact resummations of diagrams. That would be, I think, the add-on to bring compared to those studies.
Okay, any other questions? No, if not, let's thank Edoardo again.
Thank you.
And